All right, well, hello everyone, and welcome back. In this video, we're going to continue our discussion about structs and then introduce objects and classes. So if you haven't already done so, make sure that you have watched our previous video about structs so that you can pick up where we left off. Here's our goals for today's video. First, we will briefly review the structs that we covered in our previous video. You'll remember in our last video, we ended by talking about the limitations of structs. So we'll take a closer look at how classes improve upon these limitations. We'll also formally introduce classes and objects and explain how they're important and how they're used in object-oriented programming. And finally, we'll start implementing classes, structs, and objects in our programs. And we'll end with a demo on how to build a class from scratch using CLion. I highly recommend that you follow along and verify that you are able to reproduce the class that we make. Let's go ahead and get started. First, let's just briefly review what we learned about structs in our previous video. You'll remember a structure, or struct for short, is a C++ construct that allows multiple variables to be grouped together. And we saw that this is really nice for storing a set of data. And we saw that within a given struct, we can declare it such that it contains multiple different variables of different data types. So it's really convenient if we want to store a set of different variables together, we declare a struct. And we saw that example where we could take the data for a given pet and we could group all its different data, including strings, ints, and bools, all that data we could group together into a single struct. And then once that struct was declared, we could actually use that struct to create additional variables of that custom type. So we learned that structs are really convenient to use when we have variables that we want to keep grouped together as a set. In the real world, this is really useful in many applications. For example, in manufacturing or in hardware, it can be really useful to store all of the data for a given part as a struct. In manufacturing, we often need to collect a lot of data during the manufacturing process. So you have to keep track of serial numbers, part numbers, test results, where the components came from. You have to have all this traceability data. And so you could store all that data together in a convenient struct. Or in software, you might use a struct to help store a group of data for many different applications. For example, if you're making like a database, you might want to store the user profile. So you could have name, address, email, you could have all that data grouped together in a struct. Or maybe it could be a character in a game or a card in a deck. There's many different ways that you could use structs. We also learned that structs are actually pretty easy to declare and use. In order to make a struct, we use the keyword struct followed by the name that we want to give our struct. Remember, we also use an uppercase letter for the first letter of the name. This is to make it distinct from a standard variable type like an int or a double. A struct is a programmer-defined type, so often we choose to give those uppercase letters. Notice the semicolon goes at the end of the struct declaration after that closing curly brace. And then inside the braces of our struct, we list all the variables that each struct is supposed to include. In order to access data within a struct, you'll remember that we need to use the dot operator. And you might remember the dot operator from when we covered files in Lecture 6. You'll remember we used things like infile.open and that little dot there is our dot operator. We'll revisit the dot operator in more detail as we start working more with structs and classes. But for now, the thing you should know about the dot operator is that we need to use it in order to access data within our struct, or access member variables within a struct. So the syntax that we follow is we first write the name of the struct that we want to get data from. So name of the struct variable. Then we have dot, and then we have the variable we want to access. For example, if I had that pet struct, and if I wanted to access the name variable inside a pet struct, I could say, for example, pet1.name is Fluffy, and that would go into my pet1 struct, and it would access the name variable. And remember, once we use the dot operator to access those variables, those member variables can be used just like any other variable. For example, pet2.name will access a string variable. So if I say cin pet2.name, it will copy whatever input is in the keyboard into pet2.name. Let's take a look at a quick example before we move on. In this example, we've declared a payroll struct, as shown here. So this payroll struct can be used to declare payroll type variables. Each payroll type variable will contain an employee number, a name, hours, pay rate, and gross pay. Then in this line of code, we declared a payroll type variable named employee. So this payroll variable employee is going to be a struct which contains some space for an emp number. It's going to contain space for a name, hours, pay rate, and gross pay. So we've declared that payroll struct named employee. And now we want to go through and we want to update all the data within that employee struct to contain the following things. We want to set employee number to 123, name to Professor Erickson, hours to 40, pay rate to 1050, and gross pay to be hours times pay rate. If you'd like, you could try pausing the video now and see if you can write the code which will complete these tasks. Otherwise, let's discuss it together. So remember, in order to modify the member variables within a struct, we need to use the dot operator. So let's go ahead and show how that works. If I want to set employee's emp number to 123, I need to write the code employee dot emp number equals 1, 2, 3. That will go to my employee variable and go to emp number and update emp number to contain 1, 2, 3. Next we have the name. So be careful here. Remember, name is a string type. So when we are assigning a string variable, we need to put the thing we want to assign in double quotes. So here, since name is string type, we go like this. And we can do the same approach for hours and pay rate. Once again, we take our struct that we want. So we want to access our struct variable employee and the hours member variable inside, and we set that to 40. And then pay rate, we set to be 1050. Notice since these are doubles, they do not need to be in quotes. And how about this last one? Here I want to set gross pay to be hours times pay rate. Can I just go like this? Would that work? Yeah, not quite, right? Remember, in order to access the hours and pay rate variables, I need to use the dot operator. So here I say employee.hours times employee.pay rate. Notice this will allow me to take the 40 and the 1050, multiply them together, and put the result inside gross pay. So the dot operator is really important. Please make sure you understand how to use the dot operator to access data like this. And I definitely recommend checking out our previous lecture if you would like additional review. Let's pick up where we left off last time. During our last video, we ended with some limitations of structs. And we identified two main areas where structs don't always fully satisfy our requirements. First, structs are generally used only to store data. They're not used to store functions. And you might be thinking, well, why would we need to put a function in a struct? That's kind of silly. And you're right that if we have a very simple program, we probably don't need to put data and functions together. But imagine if you were working on something big and complex, or if you were working with a big team on a very detailed program. If you needed to make changes to the data and the functions in your program, it would be pretty tedious to have to go through your program line by line and modify both your structs and the functions inside that entire program. And so if you have a big program with a lot of functions and a lot of data, it sometimes can be a problem to have your data and functions kept separate. Remember, we want to be efficient. We want to be scalable. We want to write code that is easy to update and change if we need. And so it would be nice if we had the ability to bundle our data and our functions together. We'll look at another example of this in just a moment. The second main limitation of structs is that everything is public within a struct. What we mean by public is that there's no data protection. And once again, you might be thinking, well, why would we want to protect our data? And that's a fair question. For most of the programs in this course, the programs are fairly simple, and it's probably not the end of the world if we didn't have data protection. But in the real world, there are definitely situations where we don't want all parts of our program to be able to access all of our data. Here's a few examples. Suppose you're in industry working on a program with a big team. Do you want your teammates to be able to modify your data without restriction? Hopefully they wouldn't try to sabotage your program, but you never know. Probably want to be able to protect the data that your program is relying on. Another application is if you have a program that's storing really important data. You want to make sure that you have protections in place so that you don't accidentally modify important data. Imagine if you're writing a program that stores people's bank account numbers, or customers' orders, or social security numbers, or really important data that you can't afford to screw that data up. So if your program stores really important data, you probably want to have some protections in place to prevent that data from accidentally being modified. And you'd also want to make sure updates are made properly, without corrupting the data, entering invalid values, or creating other errors. You want to make your programs bulletproof and idiot-proof so that they don't accidentally get messed up if some user walks in and does something unexpected. So as nice as structs are, they're not perfect. In many situations, structs leave something to be desired. And that's why we also have classes. So last time we ended on this slide. We introduced a class. Classes are basically an improved version of a struct. Classes have additional capabilities which overcome the limitations that we just covered. Let's go through these different capabilities one by one, and then we'll look at an example to see how this helps us. So first thing that classes offer is something called encapsulation. Classes allow us to put both data and functions together within a struct-like thing. By bundling our data and functions together, we can make self-contained modular programs. And so we'll see that this can make things a lot easier when we're trying to make changes, or if we're trying to do many different, more complex functions within our programs. Also, classes give us the ability to do data hiding. When we create our classes, we can declare some items as public, where they're available to everyone. And then we can also declare items to be private. And the private items can only be accessed by members of that class. So this adds a layer of protection into our data. We can prevent people from jumping inside our struct and messing with our data. So classes allow us to have a lot more control over our data, and they also allow us to add new functions and new capabilities. You'll remember that when we create a struct, we can use that struct as a template to create different variables of that struct. If we make variables using a class, we create what's called an object. So an object is an instance of a class in the same way that a variable can be an instance of a struct. Let's take a look at an example of how classes can help us improve our data storage. We've already covered a little bit about PPM images in this course. So you may remember our PPM images from previous lectures. If you'd like a refresher, I would recommend that you go back and check out our Applications of Arrays lecture, where we covered and introduced what a PPM image is. A PPM image is one standard format used to store data for a different image. And there's many ways that we could store data for a PPM image. You'll remember in order to store a PPM image in C++, we need to store these header variables, the P3, the length and the width and the height here, and also the maximum value of a pixel. And then we also have the body of the PPM image, where we have sets of RGB values. So in this case, suppose we're trying to find the most efficient way to store data for a PPM image. And we need to store all of this data within our C++ program. The first way that we learned is to declare many variables. So we can declare a string for the P3, we can have ints for width, height, and max value, and then we can use one or more arrays to store each pixel. So this isn't a bad approach. It certainly works, but it definitely has some significant advantages and limitations. Let's take a closer look. If we wanted to store all the data for a PPM image using just a bunch of variables, the main advantage is that this is quick to implement. You just write the code here, maybe write a couple functions, and you're good to go. But if you think about it, there's actually quite a few disadvantages of this approach. First, this is not scalable. If we need to store data for 100 images in our program, we would need to declare this set of variables 100 times. We'd have a ton of variables to manage. Next, bookkeeping is challenging. When I say bookkeeping, I mean updating and maintaining our data and doing inputs and outputs. If I wanted to update the data just within a single pixel, that could require quite a bit of code and quite a few functions. If I want to do inputs and outputs with the entire image, that would also require, one or more functions, quite a bit of code in order to do that. I couldn't just write one line of code that says change pixel 5 to 000. Also, another thing to note about this is that you'll remember if I have arrays, and if I want to use functions to manipulate all this data, I would have to plug in a lot of inputs and use pass by reference to modify each of these variables separately. So it's a lot of variables to pass in and out of our functions. Keeping track of all that can be challenging. Also, the last thing to note here is that there's no way for us to easily prevent out-of-range errors or check for invalid inputs automatically. If we want to do this error checking, we would have to write error checking code every single time we make any change to our data. And that could be a little bit tedious to have to keep writing. Finally, there's no way to protect our data. If somebody accidentally tries to change our data somewhere else in the program, we have no way of preventing those changes. So as you can see, just using plain old variables here, it can work, but it's definitely not the cleanest solution. Let's look at the next possible method for storing ppm image data. A slightly more efficient way would be to declare a pixel struct and a ppm image struct. We just learned that structs allow us to group all of our data in all of our variables into a convenient set. So this definitely gives us some improvements. Here are some of the advantages and disadvantages of storing a ppm image's data using a struct. First advantage is that this is definitely a more scalable and more efficient approach. You'll remember that structs allow us to store all the variables for a given image as a single set. And so it's definitely easier to declare and modify and update data within a given struct. We just have to use the dot operator. Also, it's easier to write functions which modify or return structs. So you don't necessarily need to plug in quite as many arguments. Instead, you can just plug in a struct. But structs still have some disadvantages. It's still kind of challenging to prevent those out-of-range errors, or check for invalid inputs. We would still need to write code every single time we do an input or output in order to check for those error conditions. And once again, there's still no way to protect our data from accidentally being changed by other parts of the program. So the structs definitely make some improvements, but they're still not quite perfect. Let's now look at a third option. A third approach for storing a ppm image's data is to declare a pixel struct and a ppm image class. We just mentioned how classes can improve upon a struct. Let's briefly introduce what the advantages and improvements would be. First thing we'll notice is that we keep all the same benefits of structs. So we'd still be able to group our data into a set, but we also gain data protection. And we also gain the ability to bundle functions and data together to get even more capabilities. So you'll notice that if we use a class to help us store a ppm image, we gain a significant number of advantages. Just like with structs, this is a more scalable and more efficient solution. But notice that it allows us to group all our variables and our functions together for a given image. Like with structs, it's easier to write functions that modify a single ppm image object rather than a whole bunch of stray variables. Another big benefit of using a class for our ppm image is that you'll see that we are able to designate data as private. So you'll notice in this example here, you can see that we have put all the image's variables to be private within that ppm image class. What this means is that these variables can only be accessed by the class's member functions. So this provides a layer of protection. I would need to use these other functions like getWidth, getHeight, or setWidth, setHeight in order to go through and update that data. Also, we can write functions that add additional capabilities. Like within that set height, set width, all these other functions that we write, we could add capabilities to check for an invalid input. We could have functions to check for out-of-range errors. We could even write functions to streamline inputs and outputs into a single function. Also, we see that it's easier to make updates with a class. Instead of having to read through hundreds of lines of code in order to make a change, if we want to change the functions and data in our class, we just need to update our declaration and implementation files for the class. So it's much easier to make updates. And in the next few lectures, we're going to see another big advantage is that the external facing interface remains the same. So even if we change the class's data or functions and all the code hidden within the class, the external facing part of our class that the rest of the program sees remains consistent. And so it makes it a lot easier to make changes and updates as we go through the programming process. The one main disadvantage of classes is that compared to other approaches, it can sometimes take a little bit more time upfront to write the code and the functions for the class. And depending on what you're trying to do, a class might be overkill. For extremely simple programs, classes really might not be necessary. But you'll see that classes can definitely allow us to introduce a lot of very nice features like data protection and encapsulation. So let's go ahead and take a closer look at how we actually use classes in C++ and how we can actually build these and implement them in our own programs. Let's first begin with a few terms. Up to this point in the course, we have been doing what is called procedural programming. In procedural programming, we focus on writing functions to manipulate data. In procedural programming, a program's data and functions are kept separate. And if you're trying to do something fairly simple, this is not necessarily a problem. But as we mentioned, in big complex programs, sometimes it's not so good to have data and functions separated. It can create some issues. When we use classes in our programs, remember classes allow us to build objects or instances of the class. Just like how struct variables are declared using a struct as a blueprint, objects are the variables we create when we use classes. That brings us to object-oriented programming. In object-oriented programming, we use classes to define and create objects. Objects, since they're made out of classes, they allow us to combine our data and functions together. And so object-oriented programming is what allows us to create these sort of self-contained modular programs. And as we saw in our example earlier, object-oriented programming can allow us to have additional capabilities like encapsulation and data protection. And these features can be really important for streamlining more complex programs. Let's go through a few more terms. As we mentioned, a class is like a struct, but a class has additional features. And as we saw, these features include being able to make data private and public, and also the ability to store both data and functions together within a class. An object is an instance of a class or a variable made using a class. It's just like how a variable can be made using a struct. Often we give the analogy of a blueprint. A class is like a blueprint that describes how a house can be built. Then we can take that blueprint and we can build a bunch of houses from it. So in this case, the objects are the variables that are built from our class. Let's go through a few more key terms. First term you may hear with classes is data hiding. When we say data hiding, we mean restricting access to certain members of an object. So members could be variables or even functions. So if there's certain variables and functions that we only want other specific things to access, we can use data hiding to protect those variables and functions from all the code and instead limit access only to members of the class. Next term, public interface. The public interface is the external facing functions which allow the object to provide access to some of its data and functions. A good example of this is in a car. All cars have an external interface. The public interface of the car might be the steering wheel, the gas and the brake pedal, and maybe some of the gauges, like the fuel gauge and the speedometer. But notice that some parts of the car are kept private. For example, the engine, if you have an automatic transmission. Or things like the fuel pump, or the spark plugs. Notice that the driver of the car does not need to control the fuel pump directly. And the driver of the car does not need to know every detail about how the engine works. But every time you get into a car and you want to drive, you hope that that car has a steering wheel, gas and brake pedal, and speedometer. So the public interface here is really important because it allows us to keep certain things standard. It helps us protect the internal details about our design, but it allows access to certain data and functions that the user needs. So in a car, we can still use our steering wheel, our brake pedal, gas pedal, but the user is prevented from messing with the engine and the fuel pump because the user does not absolutely need to access those parts of the car. Finally, our last term is encapsulation. When we say encapsulation, we mean combining our data and functions together into a single package, such as the object declared from a class. Let's do a quick review question before we move on. See if you can correctly identify the false statement about object-oriented programming and procedural programming. Take a moment and see if you can find it. All right, well, let's go ahead and start with the true statements. Well, one true statement is choice A. In procedural programming, data and functions are kept separate. Choice B is also true. In object-oriented programming, we combine our functions and data together using encapsulation. And choice C is also true. We talked about the limitation of structs being that having data and functions separate can sometimes create problems for us. The false statement is choice D. Now that object-oriented programming is available, It certainly is a nice tool. However, that's not to say that procedural programming is now useless. There is certainly a time and a place for procedural programming. And for very simple tasks, procedural programming often is faster and easier to implement. But it's important to know how to do both kinds of programming. Object-oriented programming can unlock a lot of very nice capabilities that are much more challenging or even impossible to do with procedural programming. So it turns out that we have already used some classes before. For example, the string class. When we use the include string header, we give ourselves the ability to declare string objects, and we get the ability to use built-in functions like length, also getLine. Those are all important functions associated with the string class. And the include string header allows us to access the functions and ability to create string objects. Another important class which we have used before is the FileStream class. When we use the include FileStream or include FStream header, this allows us to create input and output FileStream objects. You'll remember in our file manipulation lecture, we showed that we need to declare these objects in order to be able to read and write files. And essentially what we're doing is this input FileStream object allows us to combine our file's data with the functions to manipulate that data. And you'll notice our dot operator appears again, because we are using the open function on the input FileStream object, and we're using the close function on the input FileStream object. So we've already used some classes before. These ones are built in. But we can also create our own classes. So in the rest of the video today, we're going to start looking at how to create our own classes in C++. There's one more question that sometimes comes up. Why do we bother with data hiding? Well, as we mentioned before, there are certainly times when we want to prevent people from being able to access our data without us knowing. So if we make member variables of our class private, this provides some protection. Only the member functions of a class will be able to access our private data directly. So this helps us prevent our data from being accidentally modified. So this is an important point. If you attempt to change a private member or private member variable, your compiler will return an error. So only a class's member functions can access private data. If you're not using a member function of a class, if you just have code somewhere else in your program that's trying to access a private variable, the compiler will return an error. And if you think about it, this makes sense. If we go back to that car driving example, the driver of the car doesn't really need to tell the car when to run the fuel pump. So sometimes it's okay for internal operations to be kept hidden. The last thing you want is your user to go in and mess something up without you knowing. So let's take a look at how we actually declare a class using C++. You'll notice that the declaration of a class is really similar to the declaration of a struct. There's just a few differences. So first thing you'll notice is that we use the keyword class. So instead of saying struct rectangle, we would say class rectangle. And then notice we also have to include private and public. And so notice that private is used to designate which variables are private to the class and which variables can be accessed by everyone. So we have the private and public designation. And notice that we can also include function declarations within our class. Also notice that we do have regular colons after private and public, but then there is a semicolon at the end of our class declaration. Very similar to how we have a semicolon at the end of our struct declaration. So let's take a closer look at public and private. So any items that we list as private, these items can only be accessed. Items can only be accessed by the class's member functions. So member functions are the functions declared in the class declaration. So in this case, notice the width and the length variables in this rectangle class are private. The only things that can change width and length are the functions setWidth, setLength, getWidth, getLength, and getArea. And notice that the const modifier here is used next to getWidth, getLength, and getArea, and that provides additional protection because const will not allow any data to be modified by those functions. All these functions can do is return whatever width, length, or area is calculated with those variables. But notice that anything listed in the public part of the class can be accessed by everything outside the class. So here, any other part of my program can call getWidth, getLength, or setWidth, setLength. But if I want to access width and length, I can only do so with those member functions. So once again, anything designated as public can be accessed by everything. Anything designated as private is members only. It can only be called or accessed by functions which are members of that class. Also note that public and private designations can be listed in any order, and the default setting is private if you do not specify. As we mentioned, some programmers choose to include const after the function declaration. If you include const here, this will ensure that the function cannot change any data in the object that it is being called with. So this is an additional layer of protection. It prevents those get functions from making any changes. One thing to note, if you have const in the declaration, you also need to include it. You also need to include const in the definition for each of these functions. So that just makes it consistent between declaration and definition. You remember declarations and definitions need to match. So we've looked at how we declare a class. How does this fit into our actual program? Here's an example of how the class rectangle could be written with a full main function. So there's a few important rules that you'll want to remember. First rule is very similar to structs. Typically, you need to include your class declaration at the beginning of your program, just underneath the class headers. And the reason for this is because, just like with the struct, we want that class to be available everywhere in our program. So if we declare it right in the beginning, then it's available to everything that comes after. Also notice that this declaration is global, so any functions can access. We do not put the class declaration in main. We want to have our classes typically declared globally so that everything can access them. In rule number 2, you see that generally we declare our variables to be private. So remember, the whole point of using classes is to protect our variables from getting accidentally changed. So generally, we make our variables private most of the time. Next item, suppose we now are in our main function. In this first line of code here, I'm declaring a rectangle type object named box. And so this box will automatically be declared with all of the items in our class declaration. And so notice to declare an object, we just take the type of the object, which in this case is rectangle, and then we give our object a name. It's just like ifstream infile or ofstream outfile or a string name. We've declared many objects before. Next one is this rule number 4. If we want to use any variables or functions, we need to use the dot operator. But be careful because remember, private variables can only be accessed by member functions of the class. Notice here, for box, if we want to update the width in box, we have to use box.setWidth. We can't just say box.width is rectangle width. And that's because width is a private variable. So if we want to change our private variable width, we have to use the setWidth function. Let's look at a few more points about classes. You'll notice on this slide that we just were on, we first have our class declaration, and then we have our main function. If we're putting our entire class within the same CPP file, we would need to list our function definitions after the main function. And so, again, this is using a single CPP file for the class plus the program. So there's a few things to be careful of when you are defining your functions. Remember, we declared our functions here in our class. But we still need to define in order to tell those functions what to do. So we always need to remember to define our functions at the end of our program or in a separate file. We'll look at this more in just a moment. So a couple important things to watch out for when you are defining your member functions. So remember, your function declaration goes inside the class declaration. But then notice this thing. Next to each function definition, I use this thing that contains the class name followed by the scope resolution operator, basically 2 colons. And so I call the scope resolution operator kind of the membership badge. The scope resolution operator designates that function. To be a member of the rectangle class. So here, I have to have rectangle in those 2 colons in order to tell the compiler that this setWidth function is the setWidth that needs to be a member of the rectangle class. You never know, I might have other functions. What if I have another function called setWidth that is not a member of the rectangle class? I need to be able to clearly tell the compiler which of these functions I'm defining are actually members of my rectangle class. So the class name and scope resolution operator, these tell our compiler that that function is a member function as we had declared in our class declaration. And so as noted down here, the scope resolution operator is used to tell a member function that we are a member of that class. And notice we use the class's name itself. So we use rectangle, not box. We use the actual name of the class here. Finally, notice if you check back in our earlier main function, we see that to call a member function, we use the function's name, setWidth, and then we use the object we want to call the function on. So we have the object that we're calling on. We have the function name setWidth, a dot operator in between, then we plug in any arguments. So in just a moment, we'll do a live demonstration of putting together these classes so you can see how everything is built. So this may seem like a lot of new syntax at first, and classes may seem a little intimidating when you first get started with them. But please make sure you take the time to go through the examples that we're about to cover. You'll see that after you've tried a few examples of classes on your own, and after you've started writing class declarations and implementations, it gets a lot easier. So please be patient and give yourself the time you need in order to practice writing and implementing classes. Once you understand how they work, they can be an incredibly powerful tool. But please be aware that it is normal that these have a bit of a learning curve, and it can take a little time to get used to all that syntax. So please make sure you take the time to really understand how this works and feel free to reach out if you have any questions. So finally, I'd like to finish up our video with a demo of how to build a class from scratch. In the previous example, we showed that it's possible to put a class declaration, a main function, and the function definitions all in a single file. However, you can imagine that if you have multiple classes in your program, it could start getting crowded pretty quickly. So very commonly, programmers actually use multiple files with classes. So rather than trying to squeeze everything into a single CPP file, it's very common to instead use multiple files when working with classes. You will see in our assignments for this course that most often we use multiple files when working with classes because it makes things a lot easier. And you'll see in our next few lectures as we build more and more complex programs that having multiple files really helps keep things organized. So in a moment, we're going to go ahead and demonstrate how to build a class from scratch. And you'll see that when we build classes ourselves, we are actually going to create a total of 3 files. So we use 3 files when creating a class with multiple files. So our first file is called the header file, also known as the interface file. Please note that the name of this file will always be the name of your class.h. So for example, for the rectangle class, we always name it rectangle.h. So please be aware this is an extremely important convention. Your header file will always have the class's name .h as its file name. You'll see that we put the class declaration inside this header file. The second file we create is called the implementation file. This file will always have the name classname.cpp. So for example, with the rectangle class, we name the file rectangle.cpp. So remember, the implementation file must have the same name as the class, but end in .cpp. We call this file the implementation file because it contains all the definitions for the member functions of that class. Basically, this contains all the code that tells our functions what to do. When we say that we are implementing a class, that means we are writing all the code in that implementation file so that our class's functions will work properly. So it's very important that you remember to put all your function definitions inside that implementation file. And one other thing you need to do is you need to use include classname.h to reference the header file inside the implementation file. That include header will give the compiler a heads up that it needs to remember to reference that header file for all your function definitions. Finally, the third file type that we're going to make is called an application file. The application file is the file where we put our main function and any additional parts of our program that had not already been put in the header and implementation. The application file can be named whatever you want. It could be like main.cpp or something else. But notice that you do need to use include classname.h with the quotes to reference the header file in that application file. So let's go ahead and try doing this process. Let's try building a class from scratch. So what we'll do in the next part of this video is we will follow the steps shown here. Our goal will be to build and implement the rectangle class that we looked at earlier. So first we'll create a new project in CLion, and we'll see how CLion has some built-in tools that allow us to easily make that rectangle class. We will also update our header file with the public and private members of the class. We'll also update cmakelist.txt so that our compiler knows to combine all three of our files when compiling our class. We'll also introduce a very nice tool that CLion has called Generate Definitions. So we will see that the Generate Definitions is a very nice feature in CLion, and it will automatically help create empty function definitions for us. And once we do that, then it's very easy to use the empty definitions and just fill in the code for each function. Lastly, we will update our third file in the main function in order to actually run a short program. So I highly recommend that you follow along with me as we go through and build this rectangle class from scratch. Most of the time in our assignments, the class will already be implemented for you, but if you ever want to practice on your own or build your own classes, it's really important that you understand this procedure. So let's give it a try. So our goal in this demo is to create a class. So there's a few ways we can do this. One way is to go over to my project directory. I can right-click, and I can say New Class. Another option is I can go up to File, New, and I can choose Class from there. Also notice there's some other settings that we can adjust. For example, if I want to have the dark or light background, I can do that as well. So here I'm going to go ahead and let's go File, New, and create my new C++ class. When I choose New Class, notice I am prompted with a pop-up menu. Here I'm going to go ahead and say the class's name, which is Rectangle. And in this case, I want my rectangle to have .cpp and .h. That means that CLion is going to automatically create a CPP implementation file and a .h header. If I wanted, I could just create header only, but here I'm going to go ahead and have it create both the header and the implementation file for me. Next, I click OK. So notice what happened. CLion has just created a rectangle.cpp file, and it already put in this include rectangle.h header so that my CPP file will reference rectangle.h. So notice if I open rectangle.h, that's my header file, I see that CLion has already put an empty class declaration for me. So this is where I can go ahead and put in all the code in order to declare my rectangle class. Once I have declared my rectangle class, then I can put the function definitions inside rectangle CPP. Rectangle CPP is my implementation file. And finally, if I want to write my main function to use that class, I can put my code for my main function inside this main.cpp. And the one thing, of course, that I need to remember is within my main function, I also need to include rectangle.h so that I can reference the rectangle class. Well, you'll notice I'm getting some error messages here. This file does not belong to any project target. Code Insight features might not work properly. So what this is saying is that CLion doesn't know what to do with these two files. I have not yet told CLion in order to make any executable files. So one thing I should do is I need to go into cmakelists.txt. And what you use is you use this function called addExecutable. With this function addExecutable, I can tell CLion that I want it to compile all three of my files together when running the program. So for example, in this case, I could say add an executable called rectangle class completed. And if I want it to make that executable, it needs to compile main.cpp with rectangle.cpp and rectangle.h. So this extra line here is needed to tell CLion that it has to compile all three of my separate files into a single executable in order to run my program. This is a very important step because this is how we tell CLion that it has three files to look in, not just one. Once I've added this line, I can go ahead and click Reload Changes. And you'll see now that I've updated CMakeLists, I have an additional option under my Run Configuration menu. And now I can run rectangle class completed, and that will compile all three of my class files. So now that we have set up CMakeLists, let's return to our rectangle header file, and let's fill in the code that we need in order for our rectangle class to run. So let's go ahead and first declare the private parts of our class. For rectangle, you may remember from our slides that we had private variables width and length. Then we also had some public functions that are set up in order to access the private variables. So here you want to be careful because you want to put some thought and planning into these functions. And we also have a very important convention for this course that every time I write a function declaration, I need to include precondition and postcondition comments. So notice that these public functions are what I'm going to use in order to access my private variables. For example, I can declare and define the setWidth function so that it will update my width private variable to be newWidth. So precondition here would be newWidth is initialized to a valid width value, and then postcondition, this will sets private variable width to be newWidth. So this setWidth function allows us to update the private variable width. By the same reasoning, we also need to have a function called setLength. And setLength would use some argument named length. And here, precondition, postcondition are similar. New length is initialized to a valid double value corresponding to a length. And postcondition, notice we set that private variable length to be equal to new length. So it updates our private variable to be whatever new length that we pass in. There's a few other functions that we may need to declare here. Let's next consider some get functions. Why would we need a get function? Well, remember, the only way to access the private variables in our class is by using member functions. So we have set width and set length in order to update our width and length. We also need to declare get width and get length so that we can return whatever length that we have stored. So really the only precondition for these get functions is that the rectangle object has its width variable initialized. Otherwise, you'll just return garbage. Our postcondition here is that get width will return the value of the private variable width. And similarly, get length has the same type of requirements. Rectangle object, ideally it will have that length initialized, otherwise we return garbage. And remember, our postcondition tells us what happens after the function runs. Well, this function returns the value of the private variable length. Notice it's double type, so get length has to return a double. You'll also remember we mentioned that some programmers like to include the const modifier here for the get functions. If we include the const modifier, that will help prevent the get width from making changes to variables. So get width will not be able to make changes. Const is just an extra layer of security. Similarly, get length could also be given the const modifier. So that way, that get length function, the only thing it can do is return the length. There's no way that function can go in and change something without our permission. So now we have set up this class so that we can easily access our private variables either by using the set function to update the value or the get function in order to return whatever value was stored. But right now, that's really not that different than a struct with data protection. What if we actually wanted to do some calculations with this class? One thing we could do is we could write some more functions for additional capabilities. For example, I could write a function called getArea. GetArea would require our private variables width and length to be initialized to valid values. After getArea has been called, the postcondition would be that this function returns the value, the area of the rectangle. So in this case, the area would be width times length. And notice we could write other functions too. For example, inside the setWidth and setLength, we could have some condition that requires width and length to be positive value to avoid errors. We could even include a maximum or minimum allowable width or length. So the get and set functions can actually be really important for adding extra capabilities into our program. So we've now completed our class declaration. And you can see that we have our private and public variables all listed and our function declarations completed. The next step is to go into rectangle.cpp, and we need to write the definitions for these functions. Remember, these are just the function declarations. The definitions go in rectangle.cpp. So if I wanted, I could go in here and actually just start writing these functions, right? I could say like void rectangle, and I could say set width, and notice I could go through and type out the definitions. But that's a lot of work. CLion actually has a really nice tool that we can use to help us with these definitions. Notice what I can do. I can right-click on this function, and I can go down here to generate. So I right-click on any function declaration, go to generate, and look what I can do. I can go down here to generate definitions. And then I can hold down Control, I can select all my functions that I want to create definitions for, and I click OK. And look what CLion just did. Now inside rectangle.cpp, CLion has put empty function definitions, and all I need to do is fill in these definitions with the code. CLion automatically put the scope resolution operator so that I know that each of these functions is a member of my rectangle class. So now all that's left is to go through and write my function definitions. So what should setWidth do? Well, setWidth should update my private variable width to be new width. Remember, this rectangle function, or this setWidth function, is a member of the rectangle class. So setWidth is allowed to directly access the width variable of the rectangle class. Similarly, setLength just needs to go in, and it will update my length of that rectangle to be whatever the new length was. For getWidth and getLength, we don't want those functions to return 0. What should these functions return? Well, getWidth, that should return width. That's the value of my private variable width. Remember, this function is a member of the rectangle class, so getWidth is allowed to access the private variable. Similarly, getLength will return my length. What will getArea return? Well, that's just width times length. And notice we have now successfully written the implementations for each function. So once I have defined all of my functions for a class and written the class declaration in the header file, notice now CLion's warnings went away. The rectangle class is now ready to be used in our program. Finally, the last step is for us to actually create a main function which uses the rectangle class. So to do that, let's go ahead and put some code inside our main function. So here I'm just going to go ahead and take some code from our lecture slides. You need to also add using namespace standard for C and Cout. And notice here, you can now see I've also included the rectangle.h to reference the rectangle class header. Now I'm able to declare a rectangle object in box. I've declared variables for rect_width, rect_length. And notice here, I just have some simple code that will ask my user for the width and length. And then the width and length are stored in my box object. And finally, I output the width, length, and area to the screen. So there's a couple of very important things to notice here. Notice I cannot say box.width equals rect_width. Look what happens. I will get a compiler error. Width is a private member of rectangle. So I am not allowed to update width using the dot operator in my main function. Remember, the only functions which can access my private variables are the functions which are members of the rectangle class. So I have to use the setWidth and setLength functions if I want to access the values inside my box class. Similarly, notice that I am not allowed to use cout box.width because, once again, I get the message, width is a private member of rectangle. So if I want to access my width or length, those private variables, I have to use the functions getWidth, getLength, and getArea. Please make sure you remember, private variables can only be accessed by members of that class. Any regular old code in the main function will not be able to access my private variables unless I use those get and set functions. So let's go ahead and run this code so you can see how it all works. I'm going to go ahead and choose my executable rectangle class completed. Remember, I've told C++ that it must compile all three of those files in order to run my program. And if I go ahead and run it, you see, I'm told this program will calculate area of a rectangle. What is the width? Maybe my width is 5. What is my length? Maybe my length is 10. And we receive our data. As we expect, the area of our rectangle is 50. Just for fun, you can also see what happens if we run the debugger. I'll put a breakpoint right when we create our rectangle. And notice what happens here. If we look in the debugger, we can see that we now have these private variables inside our box class. And we can track in the memory as we update values. Here, our rectangle width becomes 10. And if we ask our user for the length, 5, then notice width and length are updated in main, but notice that they're not updated in box until I run the setWidth and setLength function. And then finally, I can output our data to the screen using the get functions. get width, get length, get area. So there you have it. That is how you would put together a basic class from scratch in CLion. There's one last thing to point out before we end this demo. You might wonder, why did we bother to have CLion make the class for us? Why didn't we just write it ourselves? Notice that CLion automatically knew to include some extra code in our functions. And in the header file, we see that CLion also added this extra code for if not defined, and then define. This extra bit of code here is very important. It prevents the class from being declared more than once. So we're telling the compiler, if we have not yet defined our rectangle class, then go ahead and define it. And then this just tells the compiler that that's the end of the class definition, or the end of the class declaration. So this is a really important thing to watch out for, is if you're using a different IDE or writing your class manually, you need to make sure you prevent the class from being redeclared multiple times. So this code will allow us to ensure that our class is declared just once. Another advantage of using CLion to automatically create our class is CLion remembered to include the rectangle.h header in our implementation file, and it was able to automatically generate our function headers so that all we needed to do was write in our code. So I highly recommend try going back through this demo yourself and verify that you're able to reproduce this class. It's really good practice. So once again, in our demo, we saw that we were able to create our rectangle.h file, and we also had that extra code added in automatically to prevent our class from being declared more than once. In our class declaration, we put in all our private variables, width and length, and we also defined all of our member functions, which manipulate those private variables. In our implementation file, you saw that we wrote all our function definitions, and because we used CLion's generate definitions, we automatically knew to include the scope resolution operator next to all the member functions. That way, every member function was designated as a member of the rectangle class. We also included the rectangle.h header to ensure that the rectangle class declaration back in rectangle.h was referenced. Finally, in our main function, you saw that we also needed to include the rectangle.h in order to reference the class declaration in main. We declared our rectangle objects. And remember, we needed to use the setter and getter functions in order to modify the width and the length of our rectangle. So just a reminder, make sure you allow CLion to help you when you are writing classes. There's really nice features. So if you just use the new class option, you just enter the class name, and CLion will make the header and implementation files for you. CLion also adds that extra code to prevent your class from being declared multiple times. And it can even use that generate definitions tool in order to generate the class definitions in the implementation file. One other thing to remember is you do need to update cmakelist.txt in order to tell CLion to compile all 3 files when running your programs. One last thing to remember, those get and set functions we wrote, they're often called accessors and mutators, or getters and setters. These functions are very important because they allow us to access our private variables in a controlled way. The mutators are the set functions, set width and set length. These allow us to update a private member variable or change that private member variable to a new value. The accessors are our get functions. These allow us to return whatever variable is stored in a private member variable. Remember, it's just returning a copy of the private variable. And most of the time, we also use the const modifier here to prevent those functions from accidentally making changes to private data. Also, make sure you remember that code outside the class will only be able to access private variables by using these functions. Please do watch out for a few other common mistakes. Remember to write all your function definitions in the implementation file. For example, that was rectangle.cpp for our rectangle class. Some students run into this error called undefined reference. If you ever forget to write a function definition for a class's member function, you'll see this undefined reference error. That error just means that you need to write a definition for a function in your implementation file. All right, so let's go ahead and wrap up here for today. Hopefully now you're more familiar with structs, the limitations of structs, and how classes allow us to improve upon structs. Please do make sure you take the time to go through these materials on classes and really understand how to build a class from scratch. The syntax may be intimidating at first, but once you get the hang of it, you'll see that classes can be incredibly useful, and they form the building blocks for more complex data structures and more advanced programs, which can be really powerful. So feel free to reach out if you have any other questions on this, and we'll see you in the next video.